Alright, so let's say give you this question of a man stepping on a scale, and the question says, a man of 500 newtons steps on a scale with a spring. In equilibrium, the spring compresses to 1 centimeter under his weight. Find the total work on the spring under this compression. So we start off by drawing a free body diagram. When the guy steps on the scale, we're going to be in equilibrium at a displacement of 1 centimeters, and so we're going to have the only force that the spring's going to feel is the force due to weight from the guy. Apply our work equation here, which is given by this integral. X1 is going to be the initial height of the spring without the guy on it, so that's going to be x1 equals 0, and then we can define the up direction as positive. X2 is going to be negative 1 centimeters because it's going to be compressing. Note that for a spring force, the force is equal to k times x. That's the force applied on the spring, also known as Hooke's law. You can plug all these values in and we get this expression here, but the thing is we don't know what our k constant is currently, so we're going to have to derive it directly from the spring constant equation. The only forces in the x is going to be the weight force, and that's going to be 500 newtons. X is going to be our displacement. If you look at our diagram here, that's going to be negative 1 centimeters. We convert the position to meters because Newton is given in kilograms times meters per second squared, so we can't be dividing it by centimeters if the unit of length and the force is meters. So we plug both those values in, and then we isolate for k by multiplying both sides by 1 over negative 0.01 meters. To do that, we can divide the amplitudes into units on the left hand side, giving us this for the answer. So this is the spring constant in the spring, and so we can plug that back into our integral equation here. We can take the k constant out and then compute the integral. We can evaluate the integral from the top and bottom limit, converting the 1 centimeters into meters since the k constant has a unit of meters, so we can't multiply that by centimeters. Evaluate the top and bottom integral, we get this, and so we can plug that back in and then do simple multiplication, multiplying the units and the amplitudes, and we get this. So this is going to be the total work applied on the spring. If we look at our diagram here, we're going to have our weight force going down, which is 500 newtons. The weight force is equal to the force in the spring in this case because it is the force being applied on the spring. And then we also have our k constant, which we solved for, which is negative 50,000 newton per meter. And so the work being applied on the spring to compress it by 1 centimeter, as we just found, is negative 2.5 joules. And work being less than 0 makes sense here because our displacement is in the negative direction from the direction we defined as up, because we defined up as positive and displacement's in the negative. So it makes sense that our work is also negative. Since our force is also in the same direction as displacement, it's in the negative direction because our force is the force due to the weight, and we can see in our diagram that it's pointing down.